Hello everyone, and welcome to this week's lecture of the Deep Reinforcement Learning series. Today's lecture is on Deep Q networks, and it's lecture 3 of the series. Last week we covered dynamic programming. We spent the lecture investigating the properties of the optimal value function. The optimal value function is the expectation under the optimal policy of the return you can expect to get from any given state action pair. We derived from first principles the Bellman optimality equation, which relates the optimal value at any state action pair, Q star SA, to the optimal value at future state action pairs, S prime A prime, along with rewards, R. We introduced this idea called bootstrapping, which comes up a lot in deep reinforcement learning. Bootstrapping is to form one estimate of value from another estimate of value. And we covered the value iteration algorithm, which takes the Bellman optimality equation and turns it into an update rule that you iteratively apply to a value function to obtain a more and more exact approximation for the optimal value. Value iteration is model-based and only applicable to discrete state and action spaces. Why is it model-based? Well, it requires taking an expectation over future transitions. So it requires taking an expectation over the reward and next state S prime given a particular state action pair SA. We're going to recap both the Bellman optimality equation and value iteration shortly. Today's lecture is going to take value iteration as a starting point and see how we can go from value iteration to DQN. We're going to go from value iteration to DQN via a series of 7 transformations that I have listed here. For each transformation, I'm going to motivate it with a problem. What issue is there with value iteration, and what solution does DQN provide to fix that problem? So I don't want you to see these changes between value iteration and DQN as arbitrary and coming from nowhere. I want you to understand them as particular solutions to particular problems, and understand which of these transformations you would drop in various settings if you didn't have things that we typically want to deal with. To begin, let's cover the transformation from value iteration to batch model-based fitted queue iteration. Let's start by recapping value iteration. So the Bellman optimality equation says that the optimal value assigned to being in any state action pair is equal to the expectation taken over transitions with respect to that state action pair. So I condition on taking that action in that state and consider the transition into the next state S prime and the reward R from that state action pair. I take an expectation of this, or I take an expectation over the reward I get immediately plus discount factor, because it's one time step away, maximum over actions I could take from that next state of the value of being in that next state and performing that action. So remember, this maximum over A prime Q star S prime A prime is just the value of being in S prime, because it's saying the value of being in S prime is equal to the maximum value of any action I could perform off S prime. So what really is going on here is inside this expectation I have reward plus discount factor value of next state. So all that's happening is I'm decomposing the return or future rewards that I could get into the next step reward, R, plus a discount factor, and then the return after that. But the return after that can just be expressed in expectation as the value of being in that next state, S prime. So that's all that's going on here. I'm decomposing returns into immediate reward plus gamma or future returns. I'm replacing the all future returns with the next state value. And this expression here is just the next state value. Value iteration takes the Bellman optimality equation and turns it into an update rule. So we say, imagine that we have our current value estimate, Q old, and we want to form a new value estimate that's better using bootstrapping. How are we going to do it? Well, we take the right-hand side of the Bellman optimality equation and we plug in our current value estimate Q old. This gives us a function of S and A, right? Because inside I have an expectation here and I'm conditioning on the state action pair. So this thing on the right-hand side is just a function of SA. And I assign my new action value function to this function of S and A. And this new action value function will be superior to the old one in the sense of having a lower approximation error to the real action value. And if I keep applying this over and over again, I'm doing value iteration. And we saw a heuristic argument in the last lecture for why, if I do this arbitrarily many times, so if I keep applying this update rule, I will get closer and closer to the actual optimal action values. Value iteration uses bootstrapping because new Q values, Q new, are formed using old Q values. So we're forming an approximation to Q star using an approximation to Q star. And all that we need is that this approximation gets better over time. Lastly, value iteration requires an environment model. Why? Because when I condition on state action pairs, I take an expectation over all transitions from that state action pair. And so I need an environment model so I can say what the probability of any transition into a new state action, into a new reward next state pair is from any state action pair. It's also only applicable to finite discrete state action spaces. Why is this? Well, imagine that my state space is infinite. In this case, I can't possibly compute this expectation at every state in my state space, right? So I can only apply this when SA, the space of state action pairs, is finite, because I have to compute this value at all of those state action pairs. And if it's not finite, then I'll never be able to compute this expectation, and I'll never finish one iteration of the value iteration algorithm. So the first problem we want to contend with is when we have larger continuous spaces. This is the most pressing problem because in most real-world applications, the state space is either continuous or so astronomically large that we could never hope to finish a single iteration of the value iteration algorithm. As an example of a finite but astronomically large state space, you can think of something like chess. The number of chessboards is finite, but there are such a huge number of them that if we tried to apply value iteration, we would never finish a single loop of the algorithm. So because value iteration involves looking at every state action pair and computing the new Q value at that state action pair, it's just massively impractical for very large state spaces and impossible for continuous state spaces. Okay, so how are we going to fix this? We're going to fix this problem by saying, well, instead of computing Q values at every state action pair, what if I compute them only at finitely many, and then hope to generalize from that finite collection of state action pairs to all other state action pairs? Now, what is generalization? Generalization is the ability to accurately predict the value of something that you haven't seen based on examples that you have seen. So a large part of machine learning deals with this problem of generalization from data. We have a finite collection of data that tells us something about a relationship, an input-output relationship, and we want to predict that relationship, or rather we want to predict outputs for other inputs that we haven't seen. And machine learning has developed many different models and techniques for dealing with this problem of generalizing from a finite collection of data to potentially infinitely many data points that you haven't seen before. How does machine learning generally solve this problem? Well, it solves the problem by fitting a model to the data that you have and using that model to predict new data. So the idea is going to be, let's compute values at finitely many state action pairs, and then use this finite collection of state action pairs to generalize to all other state action pairs using a model. Let's have a model that we can fit that will generalize from the finite collection of data that we have to all other data. Okay, we're briefly going to take a pause and just discuss some vocabulary so people don't get confused. In RL, when we call a method model-based, we mean specifically that it has a model for the environment. So this first algorithm we're going to look at, fitted Q iteration, uses a model for the environment, but it also uses a model for its Q function. i.e. we're going to fit a model to the input-output relationships of state action pair inputs, Q value outputs. And that model is what we're going to call a Q model. Now, these are two separate things, a model for the environment and a model for action values. When we talk about a method being model-based, we specifically mean a model for the environment. And whether or not we're using a model for our Q function is independent of whether the method is model-based. So I just want to highlight here that model-based refers only to whether we model the environment and not whether we model the Q function. So in all the algorithms we're going to look at today, from this point onwards, we're going to be modeling the Q function, but eventually we're going to move to model-free algorithms that don't have a model for the environment. So an algorithm is not necessarily model-based just because it's using a machine learning model to generalize Q values. This is an independent fact about the algorithm. Remember that when we talk about having a model for the environment, this model can either be learned from data or it can be given to us directly from an external source. So the thing to remember from this slide is model-based means uses an environment model, not uses a Q model. Okay? Q-learning is a regression problem. What do we mean by this? Well, in supervised learning, when we try to predict the value of an output variable given a collection of input variables, we generally divide the problems into classification and regression problems. The distinction between a classification and regression problem is whether the output variable that we're trying to predict lies in one of a number of categories, in which case it's a classification problem, or is continuous, in which case it's a regression problem. So an example of this would be if we had someone's information about someone's medical data and we were trying to predict either will they or won't they have a heart attack in the next year, in which case it would be a classification problem, or what is their blood pressure, in which case it will be a regression problem. Now, Q-learning is a regression problem because it involves predicting a continuous target measure, i.e. the value of a state action pair, from state action pairs. The key idea of fitted Q iteration is to use a Q model to learn our Q function. So we're going to take a model that does regression and fit that model to the input-output relationship of state action pair inputs and value estimate outputs. Now, we can use any kind of model for regression we like here. So we could use linear regression, we could use a Gaussian process, we could use a regression decision tree, we could use a regression random forest. Any method we like for doing regression, we can use in fitted Q iteration. Okay? All that we require is some machine learning model that does regression. Okay, so now let's see the transformation from value iteration to batch model-based fitted Q iteration. First, let's recap value iteration. I'm going to write the value iteration in a slightly different way to how you will have seen it on the previous slides. And this is to make the similarity with fitted Q iteration and the differences with fitted Q iteration even more apparent. So in value iteration, we start by forming value estimates, which I'm going to denote with a Y, at every state action pair in the space. So we form Q value estimates, YSA, at every state action pair by taking an expectation over the rewards and the next states that we could transition into, using the Bellman equation to form that value estimate. So this is our R plus gamma next state value, where our next state value estimate is the maximum of all actions of our action value estimate of all action values off that next state. Then we're going to take these value estimates and we're going to set our Q function equal to them. So we're going to set our new Q function, Q new, just equal to these value estimates at every state action pair. So all I've done is separate out the normal Q value iteration algorithm onto two separate lines. First, forming the Q values, and second, setting the Q values. And I'm going to loop this process over and over again. So this will repeat over and over again. In batch model-based fitted Q iteration, we start with a number of state action pairs, which is finite. So we have capital N of these. And these are all these are a number of anchor point state action pairs of which we're going to form value estimates and then fit our model. So now we form value estimates, but we're now going to call them regression targets. And this is because they're going to be used for regression. And these regression target value estimates use exactly the same formula as the first step of value iteration, but we're only going to form them at the state action pairs in our data set. So because there are finitely many of these, we can do this in finite time, even with an infinite or very, very large state action space. So we form our regression targets yi by conditioning on the state action pair, SI-AI, and then again just applying the Bellman optimality equation as an update rule. Then, instead of setting the new Q value, which is what we do in value iteration, we're going to fit our new Q function to that input-output, that data set that we've created of state action pair inputs, regression target outputs. So one way to frame fitted Q iteration is that I'm using bootstrapping to create a data set for myself, a data set consisting of state action pair inputs and regression target outputs. And I form those regression targets using bootstrapping. After forming this data set for myself, I'm then just going to treat it like it's a supervised learning problem and fit any model I like that can do regression to that data set of state action pair inputs, regression target outputs. Then once I've done that, I'm going to loop this process again. All right, so now that we've moved into the setting where we can have continuous state action spaces, we're now going to introduce the done signal. The done signal is just a trick. It's the most conceptually easy part of any of this. And it's just a trick that allows us to set certain values to correctly ahead of time. So the second problem that I'm going to motivate the use of the done signal with is incorrect terminal values. So suppose that the next state S prime is terminal. We saw last week our axioms for computing values, and one of these axioms was that the value of a terminal state is 0. So V star, the optimal value of a terminal state, and in fact the value under any policy of a terminal state, will be 0. And the reason for this is because once I'm at a terminal state, there are no more rewards in the environment. I'm done. So the episode is ended, I can't get any more reward, and so my value has to be 0. I can't get negative rewards, I can't get positive rewards. But we saw that in fitted Q iteration, the value assigned to any state is the maximum over actions off that state of what our Q function assigns to that state action pair. But this is true for any state, and in particular, it's true for terminal states too. And so this expression will only be correct, will only be equal to 0 when the maximum of my Q values over all actions off that terminal state is equal to 0. And in general, this won't be true. In general, our Q function will assign some other spread of values to the actions, and the maximum is not going to be 0. So what can we do about this? Well, currently our value is assigning incorrect values to terminal states. We know the value at terminal states, but our algorithm is not assigning those values. So the solution is to simply force the value at terminal states to 0. Just set it to 0 ourselves. This is what the done signal does. We're going to force the value of all terminal states to 0. We introduce a done signal D, which is 1 if the next state S prime is terminal, and is 0 otherwise. So what does this mean? The done signal is capturing, it's a binary variable, it's equal to 1 or 0, and it just answers the question, is the next state terminal or not? If the next state is terminal, it's on, it's 1. If the next state is non-terminal, it's off, it's 0. And we're going to replace the next state value with the value of the next state, V star S prime, is equal to this old value estimate that we had, maximum over A prime Q old S prime A prime, pre-multiplied by a factor of 1 minus D. What effect does this factor of 1 minus D have? So Suppose that the next state is not terminal, so S prime is not terminal. In this case, D would be 0. The done signal is 0, it's off because the next state is not terminal. So this prefactor 1 minus D would be 1. And this means that at non-terminal states, we don't change our value estimate for those states at all. We don't do anything to change the value estimate of those states because the prefactor is just equal to 1. So it doesn't do anything. What about at terminal states? So if S prime is terminal, then D would be 1, so the done signal would be 1 to indicate that the next state is terminal. And then this prefactor 1 minus D would be 0. And so our value estimate at that next state would be 0. So all that the done signal does is it's a trick that allows us to force the value of terminal states to 0, which is the correct value for those states. And it leaves the value of non-terminal states unchanged. All right, so let's see how we can incorporate this into our algorithm. First, let's remind ourselves how batch model-based fitted queue iteration works. We have a collection of state action pairs, a finite collection of state action pairs for our environment. For each one of those state action pairs, we form regression targets, yi equals expectation over transitions conditional on that state action pair, SIAI, of the reward plus discount factor next state value. And then we're going to fit our new queue function to that data set that we've created. How are we going to include a done signal in this? Well, we're simply just going to change the way we form regression targets to put this 1 minus D in front of the next state value estimate. All right, so what we're doing here is making our next state value estimates more accurate by including the done signal. And then we fit our new queue function to that collection of input-output pairs. So the only thing that's changed here, the thing I want to highlight your attention to, is that we changed the way we compute our regression targets so that we are forcing next state values of terminal states to 0 using the done signal. All right, now another really important change. We're going to want to change from model-based algorithms to model-free algorithms. Why is this important? Well, it's very, very common that we don't have a model for the environment. And so this is another really important change in addition to the first one, which allowed us to go from infinite environments, which allowed us to go from only being able to deal with finite environments to infinite environments. So the third problem is that we need an environment model. Currently, computing regression targets requires averaging over all possible rewards and next states. So we condition on state action pair SIAI, and we average over all rewards and next states S prime that we could get from that transition off SIAI. And this requires that we have a model. It requires us to be able to take an expectation over those transitions. And if we don't have knowledge of all the transition probabilities using an environment model, then we're not going to be able to perform this operation. The trick to get around this is that instead of taking expectation over transitions, we're simply going to sample a single transition off a state action pair. So we're going to replace the expectation over rewards and next states by a sample of the reward and next state off that state action pair. So we imagine that we were in state SI and we performed action AI, and then from that we transitioned into SI prime and got a reward of RI. And we're going to use that single experience that we have, that single transition that we experienced, we're going to use it in this to form our regression targets in place of the expectation. Now, because we're dropping the expectation and using a single sample, we're introducing noise into the regression targets. But what we get for introducing noise is the fact that we can learn given only a collection of transitions from the environment gathered using direct experience, as opposed to having an environment model. So all we need is a collection of transitions. So all we need is a collection of direct experience with the environment, as opposed to needing a model that tells us everything that could happen of any state action pair. All right, so now let's see how we transform model-based fitted queue iteration to model-free fitted queue iteration. So first, recap batch model-based fitted queue iteration with a done signal, form these regression targets for each state action pair, and then fit our new queue function to that data set that we've created. In batch model free fitted queue iteration, we're given a batch of transitions, Si, Ai, the reward that I get, Ri off them, whether I transition into a terminal next state, Di, the done signal, and then what that next state is, Si prime. We're given this batch of transitions, and we're now going to form regression targets at every state action pair in that batch, at every Si, Ai in that batch, using that transition. So we're changing the expectation here to a sample of a transition off that state action pair. And then again, we've just got a data set that we're going to fit our new queue function to. So the change here is from taking an expectation over transitions to a sample over transitions. And this means that we don't need an environment model to compute expectations. Instead, we can learn just from a batch of direct experience with the environment. All right, now we're going to move from the batch setting to the online setting. So the fourth problem is what I call poor quality data. And what do I mean by this? So in the previous algorithm, we learn directly from experience, but it's not experience that we generate. Somebody gives us that experience for us to learn from. And in general, that experience that we're given from someone else might not be actually particularly relevant to the kinds of problems that we need to solve. So as a reinforcement learning agent, you want to learn more about those parts of the environment that you visit regularly, right? If I'm regularly at a particular point in the environment, then I need to know what the best action from that point is. And it doesn't help me to know what the best action at other points in the environment are if I never see those states. If I never go to a state, I don't care about what the optimal action from that state is. I only care about the optimal action of states that I actually go to if I'm going to improve my decision making. So what we need is experience that's relevant for us to learn. And generally speaking, experience that's relevant for us to learn will be experience that is in that portion of state space that we actually go to. So the transitions we're given might not be in the part of state space that we care about. And in general, this is going to make it hard for us to learn a lot about the problems that we actually face. The solution to this is something called a memory replay buffer. So we still need a data set of transitions from which to learn. But instead of having that data set be given to us, we're going to form that data set ourselves. We're going to gather that data for ourselves. How are we going to do this? Well, we're going to have a data set called a memory replay buffer that we add transitions to as we experience them. So we'll continually interact with the environment, and for each experience that we have, every transition that we experience in that environment, we're going to load that into this data set called the memory replay buffer. The memory replay buffer has a finite capacity, and once it's filled up, you start forgetting memories that are furthest back in time. So it starts empty, and then you experience maybe, or let's say the memory replay buffer has a capacity of 1 million experiences. You experience 1 million transitions in the environment and load each one into the memory replay buffer. So during this time, your data set of transitions is gradually growing and growing and growing until you reach the capacity of the memory replay buffer. Once you've reached that point, any further transition is no longer added into the further transitions are added into the memory replay buffer, but you forget the transitions that occurred furthest back in time. So the memory replay buffer maintains the same size after that point, and you just forget memories that are furthest back. This means that you're gradually forgetting experience that's least relevant to the current problems you have, and loading it up with experience that's most relevant to the current problems you have. So the memory replay buffer becomes filled with experience that's relevant to the kinds of behavior that you need to learn. And it occurs in the parts of state space that you actually go to, that you actually visit. Another really important part of the memory replay buffer, another function that it serves, is to decorrelate experience. What do we mean by this? So the memory replay buffer has a million experiences in it, let's say. And the experiences at the very start of the memory replay buffer from the oldest time ago will be very different to the experiences you're having now. They'll be in different parts of state space. And in general, if I look across the entire buffer, it's going to contain a very large diversity of different states and different actions from which I can learn. Why is this important? Well, if I only learn from the most recent experience that I have, from say the most recent set of transitions of 100 transitions I experienced, then this set of experience tends to be concentrated in one part of state space. It might be concentrated in a part that I go to often, but there will be other parts that I go to often that the memory replay buffer will contain, but won't be contained in this batch of 100 experiences. Why is this? Well, if I consider a lot of environments, sequential states that I go to often look very similar to one another. So for example, if I consider 100 consecutive frames of Tetris, the Atari game, these frames will be very similar to one another. Many of them will contain the same block that's falling, and many of them will contain very similar sets of blocks at the bottom that define the contour that we have to fit the block into. So if I try to learn from this collection of experiences, I'm only really going to concentrate on this one part of state space. And this means that I'm only concentrating on learning correctly at that portion. So you can think of this operation of learn from the most recent batch of 100, then gather another batch of 100 and learn from that, as sort of like trying to train your model to do MNIST, the digit classification task, by first training on all the ones, then training on all the twos, then training on all the threes. And if you try to do this, then you won't learn properly. What you need to do is decorrelate the experience. So you learn from collections of data that contain some ones, some twos, some threes, etc. So you get good at all the points that you care about at the same time. And that's what the memory replay buffer allows us to do. It allows us to get good at all of those experiences that we regularly have at the same time, decorrelating the experience. Okay, so I've told you that we're now going to interact with the environment and gather the experience for ourselves. But I haven't told you how we're going to do that. The method we're going to use for interacting with the environment is called the epsilon greedy policy. What we want is a policy that exhibits good behavior so that we can get experience that's relevant to that good behavior. So we want a policy that does as pretty much as well as we can do, so that we get into the parts of state space that we need to learn more about. But once we're in those parts of state space that we want to learn more about, we need to explore, right? We need to try out different strategies to find out what's best. So we need some policy that simultaneously does pretty good or close to as good as we can do with our current value estimates, but also explores the state space so that we can gather more information about different strategies that might be better than the current one we're pursuing. The way we're going to do this is a very naive approach. So this is not necessarily at all the best possible approach for doing exploration. I'm going to do a very naive approach where we just randomly explore some percentage of the time. So the epsilon greedy policy chooses an action at random with probability epsilon, and otherwise chooses the action that maximizes the current Q function. So epsilon here would be something like 0.05 or 5% of the time. So 5% of the time, we're going to act at random, and this is what's going to explore different actions off our current state. And the rest of the time, we're going to choose the action that maximizes our current Q function, which is going to push us into that portion of state space that we need to learn more about. Okay, so now let's move from the batch setting to the online setting for model-free fitted Q iteration. In batch model-free fitted Q iteration, we are given a batch of transitions, and we have to learn from this batch. So we form regression targets at every transition in the batch using this formula here. And then we fit the Q function to that data set that we've created of state action pair inputs, regression target outputs. In online model-free fitted Q iteration with a memory replay buffer, we have a collection of transitions that we've most recently experienced. say this is the 1,000 transitions that we most recently experienced. So n here is like 1,000, and we load these transitions into the memory replay buffer, which generally has a capacity that's much, much larger. So the memory replay buffer might be something like 1,000,000 experiences, and these new transitions, we might interact with the environment for 1,000 time steps and load those new transitions into the memory replay buffer. Then, for every transition in the buffer, not just this most recent set, but every single transition in the buffer, we're going to form our regression targets. We haven't changed anything about how we're forming the regression targets. It's the same formula. And then we're going to fit our new Q function to that data set we've created of every state action pair in the memory replay buffer along with its regression target output. So all that's changed here is where the experience from which we learn comes from. Now it comes from a memory replay buffer that is gradually loaded into during training with new experiences. And those experiences are gathered using the epsilon greedy policy. So the new transitions that we get are gathered using epsilon greedy behavior with respect to Q. So this is the only difference here. It's where the experience comes from. It's no longer given to us. It comes from the memory replay buffer. All right, now we're going to introduce deep learning. So the fifth problem we have that we're going to solve is unstructured data. So in general in machine learning, many data sets come into the category of either structured data or unstructured data. Structured data, or tabular data, is data sets that contain a number of features where each feature is by itself interpretable and meaningful, and then we have all of these features for every individual in the data set. So biometric measurements is a good example of tabular data. We might have a collection of biometric measurements such as someone's weight, their height, their resting heart rate, their blood pressure, the level of insulin in their blood, and each one of these features by itself is meaningful. It means something. And we might have these features for every individual in our data set. And then, so we can arrange this data set into a big table. And this is a very natural way to arrange it. This makes it structured data. The fact that we can put it in this tabular format where the rows are indexed by individuals and the columns are indexed by different features that we can measure for those individuals. In contrast, much of reinforcement learning deals with unstructured data. In unstructured data, individual parts of the data aren't necessarily meaningful by themselves. Good examples of unstructured data are text, where an individual letter or word doesn't mean a lot by itself, or images, where individual pixels don't mean a lot by themselves. It's only in the context of the surrounding pixels, or audio waveforms, where an individual pulse of the waveform might not be particularly meaningful. It's also typical that in unstructured data, there is like an arrangement of the different parts of the data to give relationships between it. So in text, words are positioned next to other words. And so it's not just a bag of words, it is an ordered list of words. In images, it matters where the pixels are. Each pixel has a location, and it matters where it is relevant to other pixels. And in audio waveforms, it matters where that pulse is and what pulses are next to it. So we also have in unstructured data this notion of closeness or topology to the data set itself that doesn't exist in tabular data. There's no sense in which resting heart rate is closer to insulin levels than it is weight. So lots of environments have state spaces that are unstructured. Atari, for example. This uses Atari frames, which are unstructured data. And what we need is a model, a regression model, that can learn well from unstructured data. So I discussed a number of different models you could use for fitted Q iteration. You could use Gaussian processes, decision trees, linear regression. But in general, these aren't really good at unstructured data. But we know a method for regression that is really good at unstructured data, and that's deep learning. So neural networks are really good at dealing with this kind of unstructured data. They're great at dealing with text, they're great at dealing with images, they're great at dealing with video. So what we're going to do is use a neural network for our Q function. Now, there's two possibilities for the architecture of this neural network we're going to use. One possibility is that which is the route that's taken by neural fitted Q iteration, the next algorithm we're going to look at, NFQ, neural fitted Q iteration, is that our neural network will take in state action pairs and output a value estimate for that state action pair. Another possibility for the architecture, which is the one used in DQN, is that we're going to take in states and output a value estimate for each action of that state. So when we want to know the value of a particular state action pair, we feed the state in, we look at all of the value heads, so all of the different value estimates for all the actions, and just choose the one that corresponds to the action that we care about. Why is DQN's way of doing things better? Why is this a better architecture? Well, the reason it's a better architecture is that in DQN, typically when I'm computing value estimates, I want to compare those value estimates. So situations in which I want to compare value estimates, when I'm choosing my greedy action in my epsilon greedy policy, I need to compare the value of all actions of the current state I'm in, right? So it makes sense that I compute all of those values at the same time using a single pass through the neural network rather than doing one pass through the network for every different action. Another situation in which I'm comparing values is when I'm taking a maximum over next step actions, right? Which again, this maximum over next step actions requires me to compare the values of the different actions off the next state. All right, so now let's go from FQI, fitted Q iteration, to NFQ, neural fitted Q iteration. So online model-free fitted Q iteration using a memory replay buffer, we're going to load a collection of new transitions that we gather using the epsilon greedy policy into the memory replay buffer. And then for every transition in that buffer, we're going to form a regression target using this formula, and then we'll fit our new Q function to that data set that we've created. How does neural fitted Q iteration change this? Well, now we're just going to specify what model we're using. And I'm also going to introduce some new notation. So we now know that Q is going to be a neural network. And so we're going to index it by a set of parameters, which I'll denote phi. And the old set of parameters will be phi minus, and the new set will just be phi. So phi minus corresponds to Q old, and Q new corresponds to phi. I also haven't really specified what I mean by use a neural network, so we're also going to specify that here. So we're going to use the epsilon greedy policy with respect to our current Q function to load transitions into the memory replay buffer. Then, for every regression target in that buffer, we'll use the same formula for computing regression targets, except now I'm just changing notation, right? I haven't done anything about the formula. I'm just changing notation. So instead of writing Q old, I'm going to write Q with my old set of parameters, phi minus. Then, when I want to fit, so 3 and 4 here are going to replace 3 in fitted Q iteration. So fit the new Q function to the input-output pairs. So our new Q function is going to involve first initializing a fresh neural network, and then fitting this new neural network to this data set using an L2 loss function. And we're going to do this by typically mini batch gradient descent on that L2 loss function. So what's changed? Now we've just changed that we're just going to fit a new Q function for any Q function to specifically fitting a new freshly initialized neural network using an L2 loss function. All right, we're nearly there. So you might already be wondering, why is it that we initialize a new neural network? Well, we do that because that's what NFQ does, but this doesn't actually make a whole lot of sense, right? Because our current neural network that's computing Q values is probably doing an all right job. It probably knows that certain states are pretty good and that other states are pretty bad. And the fact that it might not know precisely how good or bad, it does not diminish the fact that it does have a good grasp on what's high value and what's low value already. So in standard NFQ, at each round of the algorithm, you train a new randomly initialized neural network. But this wastes all the training you've already done. You already have a neural network that can do a good job, and you're going to throw it away after using it to form regression targets. And you're going to need to train your new neural network for a long time to get it to the same quality that the old one has. And this is a very inefficient way to train. And so instead, what we're going to do is continuously fine-tune the same network. So instead of training a new neural network, we'll fine-tune our current network. This means continually training the same network throughout learning. So in NFQ with fine-tuning, let's briefly recap the neural fitted Q iteration algorithm. I use an epsilon greedy policy to gather transitions, and I load these into the memory replay buffer. I form regression targets for every transition in the buffer. Then I initialize a new neural network, and I fit that new neural network to the dataset I created using an L2 loss function. In neural fitted Q iteration with fine-tuning, I'm going to sample transitions using epsilon greedy policy, load them into the memory replay buffer, form regression targets using the same formula, but then I'm going to just fine-tune my current network, Q, SA, phi, on that input-output pair using the L2 loss function. Now, what's phi minus here going to be? Well, at the end of this, I'm going to load load my new neural network parameters into the old network parameters phi minus. All right, so all I've changed here is that instead of initializing a new neural network, I'll continually fine-tune the same network and then regularly and then at the end of that fine-tuning step, I will load the network parameters into phi minus. All right, this is the final transformation. It's going to take us from NFQ to DQN. The last problem is update delays. So currently, we separate out phases of gathering new experience and loading it into the memory replay buffer and fine-tuning the neural network. These happen in two separate phases of the algorithm. This means that during phase 1, your Q function is never updated. And this means that if you get experience that tells you that you should be doing something different, you're not going to update your Q function and you won't change your behavior. So this will generally lead to suboptimal action choice. The solution to this is to interleave training and sampling. So instead of having a separate phase of gathering experience and fine-tuning the neural network, we're going to alternate those two steps on a very, very quick timescale. So we're going to do a bit of one, then a bit of the other, then a bit of one, then a bit of the other. And we're going to keep alternating on this very fast timescale. Specifically, we'll gather around 10 transitions and then fine-tune the neural network by doing a single update step on a single mini batch of data. All right, we're now in a position to go through the entire DQN algorithm. We start with the synchronization step, where we load target network parameters, phi minus. We load into these our current network parameters, phi. Then, we're only going to do the synchronization steps around every 1,000 fine-tuning steps. So all concrete numbers here, the 1,000, there's another concrete number for the mini batch size. These are hyperparameters for the algorithm, and they can be played with. So the algorithm is independent of what values you set these concrete numbers to, but I wanted to make things concrete to make it easy to imagine what the magnitude of these numbers should be and how the algorithm works in a standard implementation. So for every 1,000 fine-tuning steps, we're going to alternate interaction and fine-tuning. Interaction is going to be interact with the environment for 10 steps using an epsilon greedy policy with respect to your current Q function, Q, SA, phi. For each transition you experience during those 10 steps, so each of these 10 transitions you experience, you're going to load it into the memory replay buffer. Then you're going to do a single fine-tuning step where you sample 32 transitions from the memory replay buffer. And then for each one of those transitions, each one of those 32 transitions, you'll form regression targets. And you'll do that using the same formula we've seen for all of the other ones. The regression target is the reward plus discount, 1 minus done, that sets next state values for terminal states to 0, maximum over next states that could be experienced, maximum over next actions that could be taken of the Q value at that next state of that next
next action under the old network parameters. And then you perform one update step of the parameters phi by fine-tuning QSA phi on the input-output pairs that you've generated using an L2 loss function. You do one step of mini-batch gradient descent on an L2 loss on the dataset that you have created of state action pair inputs, regression target outputs. And you're going to loop this process, interacting and fine-tuning. You're going to loop this 1,000 times, and then you're going to update your target network parameters is the synchronization step. And then you're going to loop this 1,000 times again. And if we loop this whole thing, this gives us the DQN algorithm. Thank you very much for listening.